So we have two special logs. The common log is log base 10. So if you ever see a log without a base, that's base 10. And the natural log, whenever you see ln, that is log base e. So you can use a calculator to find these values. You need to find the button on your calculator. It literally says log. So log of 10,000 is 4. Log of 341 is 2.53. Log of 0.06894 is minus 1.1615. Now, chemistry uses logs, and we'll do something interesting in class. And it defines pH as minus log of H3O plus. You remember when pH is 1, that is very acidic. When pH is 14, it's very alkaline. And a pH of 7 is considered neutral. So I want to find the pH of a solution with H3O plus concentration is 6.8 times 10 to the negative 8. So pH is minus the log of the concentration of H3O plus. So it's minus the log of 6.8 times 10 to the negative 8. So we can use the log properties. You're going to need a calculator to do these. So it's minus, let's see, log of 6.8 is 0.8325. Log of 10 to the negative 8 is negative 8. So this becomes about 7.2. Find the hydronium ion concentration in a solution with a pH of 4.3. That's the H3 plus. Okay, so I'm going to substitute in 4.3 is minus the log of H3O plus, multiply by negative 1. I want to get rid of the log, so I'm going to write it in exponential form. So H3O plus is equal to 10 to the negative 4.3. Using a calculator, you get it is approximately 5 times 10 to the negative 5. Now, wetlands are classified in the table. So a bog has a pH less than 3, a poor fen is from 4 to 6, and a rich fen is from 6 to 7.5. The hydronium ion concentration of a water sample in a wetland is 4.5 times 10 to the negative 3. What kind of wetland is this? Remember, pH is minus log of the concentration of H3O plus. So that's minus the log of 4.5 times 10 to the negative 3. Doing the computation, it's about 2.3. So this wetland is a bog. Now in physics, when we're doing sound, we talk about decibels. And the decibel scale is a logarithmic scale. And it's defined to be 10 times log of I over I naught, where I naught is the threshold of hearing. And depending upon your units, it's either 10 to the negative 12 watts per meter squared or 10 to the negative 16 watts per centimeter squared. The good news is I'm either going to tell you what I naught is or I naught is going to cancel. So find the decibel rating of sound with an intensity of what? 10 million. So D is 10 log base I over I naught. So this is 10 million times I naught. That's kind of hard to read. So D is 10 log of I over I naught. I'm going to substitute in I. I is 10 million. And you see these I naughts are going to cancel. So you're going to have 10 times the log of, really big number. So that has 7 zeros. So that's 10 times 7 or 70. So this sound has a decibel rating of 70. Now you can use a calculator to find these values. E to the fourth is, our natural log of e to the fourth is 4. Natural log of 341 is 5.8. Natural log 0.06894 is minus 2.1615. 6, 7, blah, blah. Now, by measuring the amounts of potassium, 40 K, and argon, 40 A, in a rock, the age T of a rock in years can be found with this following really ugly formula. How old is a rock sample when A is equal to K? Well, when A equals K, then A over K is equal to 1. All right. So this becomes 1.26 times 10 to the 9th times the natural log of 1 plus 8.33 times 1 divided by natural log of 2. So we get 4.06 times 10 to the 9th. So the rock is about 4 billion years old. How old is a rock sample when A over K is 0.32? 5. Well, when A over K is 0.325, we're just going to substitute in 0.325 here. And we get about 2.38 billion years old. Now, carbon dioxide in the atmosphere traps heat from the sun. The additional solar radiation trapped by carbon dioxide is a radiative forcing. It's measured in watts per square meter. In 1869, the Swedish scientists modeled the radiative forcing R caused by adding additional atmospheric carbon dioxide using the logarithmic scale. So R is K, natural log of C over C naught, where C naught is a pre-industrial rating of amount of carbon dioxide, and C is the current amount of carbon dioxide, and K is your constant. Suppose that C is 2C naught and K is 14. Find the radiative forcing under these conditions. Well, substituting into my equation, I see the C naughts are going to cancel. So this is R is about 14 natural log of 2, or 9.7 watts per meter squared. Average global temperature increase in Fahrenheit is given by T of R as 1.03 R. Find the average global temperature increase to the nearest degree under the same conditions. So T of 9.7 is 1.03 times 9.7. So it's about 10 degrees Fahrenheit. The average global temperature increase is going to be about 10 degrees. Suppose we have any positive real numbers, A, B, and X. Then if I have log base A of X, I can do what's called a change of base to any other base I wish. And they will always give me the same answer. So log base A of X is log base B of X divided by log base B of A. Use the change of base formula to approximate to 4 decimals each log. So log base 4 of 20, I can change that to any base I want. So if I change it to natural log, it's natural log of 20 divided by 4, which is 2.1610. Or I can change it to log base 10 of 20 divided by log base 10 of 4, and I should get the exact same answer, and indeed I do. Log base 2 of 7, we can use natural log of 7 divided by natural log of 2 is negative point, that's a 0.7, negative 0.516. Or we can use log base 10. So now the log base 10 of 7.7 divided by log base 10 of 2 is minus 0.5146. Now, one measure of the diversity of a species in a community is modeled by H, where P are the proportions of a sample that belong to each of N species found in the sample. Find the measure of diversity in a community with 2 species where there are 60 of one species and 140 of the other. So 60 plus 140 is 200. So P1 is 60 divided by 200, or 0.3, and P2 is 140 divided by 200, or 0.7. So h is minus 0.3 times log base 2 of 0.3 plus 7.7 times log base 2 of 0.7. You can use a change of base formula and a calculator. And you get this as about 0.881.